Hi, my name's Chris Henretti, and I'll be giving this short presentation on how to generate realistic party systems. And I want to start with a quote from the American physicist Richard Feynman. When Feynman died, he had on his blackboard the quote, "What I cannot create, I do not understand." And I think that quote is correct, and I think it's a shame that not many political scientists try to create or simulate or generate the kinds of things that they study. I think that holds in general, and I think it's also true of people who study party systems. There are certainly some people who do agent-based modelling. That's one way of generating party systems. But agent-based models are usually described as stylized, which I interpret as another way of saying not particularly realistic. And so in this presentation, I'm going to be talking about a way of simulating realistic party systems, which is going to give us a party system with a fixed number of parties, where those parties have different shares, and where parties have positions on an economic left-right spectrum. And I'm doing this for two reasons. First, because I think it's just useful and valuable in its own right. But second, because I think that if we can generate realistic party systems, characterized by a set initial number of parties, then we can start looking at how, in simulated party systems, the number of parties is related to things that we really care about, things like the congruence between the median party and the median voter, or the polarization of party positions. And if we can generate those expectations in silico, we can then go on to test them using real-world data. And to anticipate what I'm going to argue, the four mechanisms that I think are key in simulating realistic party systems are: first, that party positions should be weakly centred on the position of the average voter, that they should be repulsive, that they should be increasingly variable or dispersed or eccentric as we move from larger to smaller parties, and that whilst these mechanisms govern all but the largest party, the positions of the largest party, well, they are initially bimodal. They don't come from a single distribution, but rather a mixture of two distributions. So I'm going to describe those mechanisms. I'm going to describe some training data that I've used to calibrate the strength of those mechanisms, and then I'll describe how we can generate systems and systems with party seat or vote shares from scratch. And then at the end, I'll give you a chance to decide whether you think that the systems generated through this method are at all realistic. So let's start with these mechanisms. And the first mechanism is the dependence on the position of the average voter. And this is necessary if we want to make sense of differences between different countries' party systems. I'm simply going to assert at the moment that the average voter in Australia is to the right of the average voter in Sweden. And for that reason, it would be pretty odd if Australian voters ended up with parties that were all the way over where the Swedes are. But this dependence on the position of the average voter is never going to be exact. And as the position of the average voter moves from left to right or from right to left, party positions might not fully update. And so that dependence is going to be of different or greater or lesser strength. So whatever else is going into party positions, here denoted with the Greek letter theta, those positions are going to depend on some overall intercept plus some coefficient that multiplies the position of the average voter, here indicated by an x with a tilde above it. That coefficient, assuming that we can measure voter and party positions on the same scale, that coefficient is going to be somewhere between 0 and 1. It's going to be 0 if there's absolutely no relationship between these two things. And it's going to be 1 if these two things move in absolute lockstep. That's to say, for each one pace that the average voter moves to the right, all the parties move one pace to the right. In practice, that coefficient is going to be somewhere between those two extremes. The next mechanism is what I call repulsion. Now, lots of things can be repulsive. In the case of parties and their positions, I'm going to claim that parties are repulsed away from the share-weighted average position of all parties larger than them. So we're starting with the largest and working our way down. And we can get a good intuition for that by just thinking about the position of the largest party and then asking ourselves, well, where do we think that the position of the next party is going to be? If our largest party is somewhere to the right of the median voter, here given by this dashed line, if they are on the right, then what are the chances that the next party is also on the right? I would have thought they might be pretty low, and that the position of the second party is much more likely to be in the space to the left of the median voter. Now we can try and generalize that to think of what is going to impact all parties as we move between them. So I'm going to talk about a kind of running average of the system position. I'm using, again, this Greek letter theta, but I'm using it with an asterisk to record the position up unto party J. And that we create by taking each party's position, multiplying it by its share, adding it up, and then dividing by the sum of all the shares that we've seen up to that point. And we can work through a particular example. Here I have the results of the 2015 UK general election. You can see the largest party, the Conservative Party, is to the right. And so if we are creating the system position, that carries across straight away. We then get the Labour Party to the left, and that brings the system position to the left, still to the right of the median voter. And as we add other parties, since those parties are mostly to the left, the system position moves closer to the left, that is to say, closer to the 0 point and to the negative numbers that lie beyond. Now, most of the time, we won't be interested in the system position directly. We'll be interested in the lagged system position, trying to predict, let's say, the position of the Labour Party using the system position of all larger parties, which in this case is just the Conservative Party. So whatever else is going into the position of the jth party in the system, it's going to depend on some coefficient, and here I'm using the Greek letter rho for repulsion to stand for that coefficient. That coefficient is going to multiply the system position up to that point, but not including the party, the position of which we're trying to explain. And again, if we're measuring everything on the same scale, then this parameter is going to be somewhere between -1 and 0. If it's 0, then there's no relationship between the position of the party we're trying to explain and the position of all the parties that came before it. If the coefficient is -1, then the system position of all parties larger than the party we're interested in is, in some senses, the mirror image of where we expect the next party, the party we're interested in, to end up. And the final mechanism which concerns all parties is this idea of increasing variability. And here we can go back again and think about our predictions for the first and second party. If we know where the first party is, well, we'd probably say that our guess for the second party is probably going to be on the other side of the median voter. We're probably going to allow a small chance that they end up on the same side of the median voter. We also want to allow a small chance that they're very far off to the left. And that seems like a reasonable guess for the second largest party. But for the last party, the very smallest party that we're considering, well, by the time we get to that last party, all bets are off. The party might be somewhere over to the left, but it might be somewhere way out to the right, way out to the left. And so our guess for the last party is going to be much more dispersed. And so formally what I'm doing is I'm allowing the standard deviation of the distribution that I'm using to model party positions, I'm making that depend on the share of each party. So those mechanisms apply to all parties, but there's a special role for the position of the first party. And here, well, when I've presented this in person, I get some raised eyebrows at the claim that Anthony Downes is wrong on this. Downes famously argued that under certain conditions which are quite demanding, then the two largest parties should move to the position of the median voter. Now, empirically, that's not true. The positions of the largest parties are generally moderately far from the position of the median voter. And when I say moderately far, what I mean by that is if we're working with standardized units, that's to say positions with a mean of 0 and a standard deviation of 1, then we expect the largest parties to be plus or minus 3/4 of a unit away from the median voter, or equivalently 3/4 of a standard deviation away from the position of the median voter. And that ain't nothing. In operational terms, we can understand that by modelling the position of the first party using a mixture model. That's to say, we don't just predict the position of the largest party using a single distribution, but two distributions, one of which is on the left, and which is comprised of an overall intercept plus some coefficient, which multiplies the position of the average voter, minus some offset. So here I'm using the Greek letter omega for offset. And that offset is subtracted in the case of the left-leaning distribution, because we want to move to the left of the number line, and it's added on to the right-leaning distribution, because we want to move to the right of the number line. And similarly, we allow the standard deviation of these two distributions, these two mixtures components, we allow that to depend on the share. In general, when you have a mixture model, you can model the mixing parameter, but in our case, this ends up pretty close to 50-50. So to recap, I'm arguing that party positions can be modelled as though they were draws from a normal distribution, where the mean of this distribution depends on some overall intercept, the position of the average voter, and the position of all parties larger than the party we are interested in. The variance of this distribution depends on the share, so that smaller parties have positions which are more variable, even accounting for the things which affect the mean, and that there is a special rule to follow in the case of the largest party. That party's position comes from a mixture of two normal distributions, and that means that the largest party is going to end up on one side of the median voter, and that sets the whole ball rolling. It sets up the mechanism of repulsion that follows. So those are mechanisms which I could use as it stands, just by picking some numbers, but obviously I want to use numbers that are realistic. That's the key word of this presentation. So I need to calibrate some of the coefficients in these mechanisms. And to do that, I need good measures on party positions. There are lots and lots of data sets out there which record party positions on some left-right scale, typically an economic left-right scale. And those different data sets cover different parties in different countries at different time intervals. And so what I do is I try and combine these sources as far as I can using a dynamic latent trait model. And the advantages of using that model are simply that it allows us to combine in a reasonably sensible way all these different sources of information. And the product of that model is a standardized measure, something which approximately follows a normal distribution with a mean of 0 and a standard deviation of 1. So those are our party positions, but how can we work with voters? Well, in order to get you where I need you to be, I need to ask you a little trivia question. I want you to think about all the very many survey respondents to the 2019 Australian National Election Study, all of whom were asked to place themselves on a 0 to 10 scale from left to right. So take a moment to think, what do you think the position of the median voter is in that study? I might be able to give you a clue by asking you another trivia question, this time for a different election, held the year before, held in a different country. And yet another trivia question, same country, 30 years before. Or I could ask you the same question for Australia, 30 years before. Because the answer to all of these questions is the same. Whenever people are presented with a 0 to 10 scale, the median response is almost always going to be 5. And so what we need to do is we need to make sense of these responses given what we know about the party positions as estimated by experts. And so the idea is that we want to model each individual respondent's way of using the scale. We want to say, well, you, and here I'm imagining some hypothetical respondent in 1987 in Australia, well, you've placed this party, which we think is at position 0.63, you've used a 6 to record that. And there's this other party that we think is at a position of minus 0.2, and you've used a 3 for that. Okay, so we know those two things. We know you use the scale in that way. And if that's the case, then when you say that you yourself are 5, that might mean that you're at something like a position of 0.2 yourself. Now, that's the informal presentation. Formally, we can do this by estimating a multi-level ordinal probit model. Now, it's a multi-level model because here we have judgments from multiple parties which are all nested within respondents. So for any given respondent, we might have anything between 2 and 12 parties that they've been asked to place. And it's an ordinal probit model because we might think that the gaps between 5 and 6 are not the same as the gaps between 9 and 10. And in this model, because it's a multi-level model, each respondent has a separate intercept and a separate slope. That's to say, they can shift parties along. They might want to use 7, 8, 9, when another person would use 5, 6, or 7. They can also scale things differently. There might be some people who are very, very happy using 0s and 10s, and other people who try and cluster their answers much closer to 4 and 7. So we run one model for each country year. We work out the slope and the intercept, and then we flip the model round and we ask, okay, for this voter who used the scale in this way and reported a 5 or 6 or 3, whatever, what is their position on the scale of the parties? So I've now got my ingredients. I've got measures of party positions. I've got measures of the position of the average voter. And I'm estimating a model of party positions, which has got lots of different things going on. I've got different components. We've got a model for the first party. I've got models for all other parties, or rather model components. We've got some modelled variances. We've got some measurement error, which I haven't really talked about. And And because the number of parties differs between countries, and because I don't want countries with lots of parties to dominate the model, we're weighting by shares, either vote shares or seat shares, doesn't really matter which. And we're estimating that model on roughly 3,000 party positions, fewer if we're just using seat-winning parties. And we're trying to learn about some of these parameters. We're trying to learn about the overall intercept. We're trying to learn about the dependence on the position of the median voter. We're trying to learn how much parties repel one another. And we're trying to learn how far the first party is to either side of the median voter plus some intercept. So I'm not going to spend too long talking about the results, but I will just note that the dependence on the position of the median voter is pretty close to its maximum realistic value of 1, slightly smaller for the position of the first party. That the repulsion parameter is also pretty close to its lower bound. So parties almost repel one another fully. But one of the interesting things is that there's actually quite a sizable rightward shift, which affects the second to last parties, slightly smaller in the case of the first party. Now this is very useful, but it's a model which is estimated using real-world data, and that's not what I promised you. I promised you a way of generating systems from scratch. And I can do that as long as I'm able to set the initial number of parties. So I'm going to stipulate at the moment that we're dealing with a party system which has 7 parties in it. And our task is to reason about the share of the largest party. We know it can't be any bigger than 1, right? That might happen if the largest party wins all of the seats. Pretty unlikely, and so that's our upper bound. But we also know that the largest party can't win less than 1/7 of what's on offer. If it won less than 1/7, then there would be another different party which was the largest. And so this would happen if all 7 parties split the vote or split the seats equally. And where we have a lower bound and an upper bound, Renta-Capera has argued that often our best guess is not the arithmetic mean of these two things, but rather the geometric mean. We take our lower bound, we multiply it by our upper bound, and we take the square root of this expression. And in the example I've just given, where we've got a lower bound of 1/7 and an upper bound of 1, that geometric mean works out to just under 38%. We've done that for the largest party, but we can repeat this exercise now for the second largest party, understanding, of course, that now we're working with a remainder. What we have to allocate is not 1, but 1 minus what we gave to the largest party. And so just as before, we can set up a lower bound, we can set up an upper bound, and proceed through the same steps, getting for the second party a share of just over 1/4. And because there's nothing special in the reasoning for the second party, we can proceed throughout the remaining parties until we end up with the last party of 7 winning just over 1%. Now, in that example, gave point predictions. I gave a single share for each party. But we can embed these predictions within a particular distribution. And in particular, we can embed them in a Dirichlet distribution, a distribution which is suitable for compositional data like this, which must sum up to 100%. So this is something that I've done in previous work with Dennis Cohen. On the right, you see a kind of fan plot showing the distribution of outcomes for parties in a 7-party system. And so what I'm doing with this model is, in a sense, flipping the whole logic of understanding party systems. I'm going to start with what parties won, whether that's seat shares or vote shares. And then I'm going to generate positions which are consistent with those shares. And so the way that I explain things is not the causal sequence. It's not the way in which things came about. Because in the real world, we know that parties first adopt positions and then have people vote for them, at least partly on the basis of those positions. But this approach of flipping the logic has been oddly successful. And you might want to think about the 2017 book by Ren Tagabera and Matthew Shugart entitled Votes from Seats, where they adopt a similar move. They start from the more constrained quantity. They start from the seat distribution and then work out, okay, what might have been the vote distribution that gave rise to that? Now that makes sense in that book, but it flips the logic because people vote first and then seats are allocated. So I've described how I can calibrate some mechanisms and how I can generate shares from scratch. This allows me to generate party systems, but the question is, are these realistic? And so I would now be able to give you an example party system where there's a first largest party out to the right, labelled G here. The second largest party is on the left, and we've got parties of different sizes in between those two parties. So take a guess now as to whether that is fake or real before we move on to the next example, which is a slightly more complicated party system. Here, the largest parties are not on the extreme wings. They have flank parties to their left and to their right. There's one very small centrist party. So again, think to yourself, is that fake or real? Before thinking about the final example, which is much closer to a kind of 2.5 party system. Again, think whether that's fake or real. And if you said real to any of those, then I've fooled you on at least one occasion because all of these examples have been fake. Now, you might be wondering, does that hold generally for people who are looking at more than 3 examples? Well, I asked a number of attendees at the Political Studies Association Elections, Public Opinion Parties annual conference to evaluate 7 countries' party systems. I made them fictitious by giving them invented names. They had to say whether the 7 party systems I gave them were fake or real. On an average, half were fake, half real. And of all the guesses, the average proportion that were correct was roughly 55%. So slightly better than chance, but not significantly so. And so I'm using that as some support for my claim that these party systems are realistic. It is, of course, possible that had I asked more people or presented the same people with more stimuli, then I would have got a narrower confidence interval, and I would no longer have been able to claim that the difference was not statistically significant. Still, I think it's notable. And so my conclusions are that we can generate party systems by starting with generating shares and then generating positions that follow. And I think that these simulated systems are plausible. And so in that sense, I think I've achieved one of my goals, but there is a remaining task ahead, which is to use these simulations to generate expectations about other properties of party systems, which can then be tested on real-world data.